Okay, sorry. Yeah. So I was just saying, I have to start with this slide because this gives us sort of the zoom out view of how sort of baryon cycle works on galaxy scales, right? You have gas flowing in, some stuff happen in the middle that are miraculously giving us stars from gas, and then things flow out. And Laura's talk has highlighted that, the hot gas and the X-rays are a wonderful way to probe that outflow and this kind of cycling on the galaxy scale. But of course, when I'm talking about baryon cycle, actually what I mean is not this large scale view. I actually mean the smaller scale view that we really care about for nearby galaxies, because this is something that we can resolve, and this is really important for sort of setting the small scale physics that govern sort of the behavior on larger scales, right? So here is sort of basically another version of the slide that Laura showed, slightly more artistic, slightly less information rich. But basically the cycle we care about is this sort of rapid cycling on small scale, roughly 10 to 100 parsec scales, going from diffuse atomic gas to dense molecular gas to the formation of stars and star clusters, and then to the feedback, returning everything to the ISM, right? So this is sort of the general kind of baryon life cycle that we care about. And because of the vast range of phases the material is cycling through, so we really need multivalence of the regions, right? So this is something Laura has also mentioned, so I won't dwell too much into there. And that is why sort of the FANGS team has been furiously gathering data from all the kind of telescope that we can put our hands on. So the ALMA, MUSE, HSC, and GWST, Laura has highlighted, this is sort of our 4 pillars that have been here for a while. And then Laura and the X-ray science group that she's leading is giving us this wonderful addition on the high energy X-ray side. And sort of addressing some of the questions that appeared earlier, we also just landed a Meerkat legacy program looking at the H1, right? So basically the cold atomic gas. So with that whole range going from radio all the way to X-ray, we now really have a full view of like all the cycles, all the phases that the cycle involves. And this really gives us this sort of ability to probe all the different stages of the baryon cycle and really understand the physics that are hiding in there, right? So I myself is a long wavelength astronomer, so I'm gonna just focus more on the long wavelength side, and by long wavelength I mean everything that is longer wavelengths than infrared, right? So that would be infrared, millimeter, and radio. And I would say over the course of the past years, this wonderful data set led us to be able to create statistically significant samples of molecular clouds, star clusters, H2 regions. So these are the building blocks of the baryon cycle as we all care about in galaxies, right? And this statistically significant sample across this large sample of galaxies really taught us a lot of things about how baryon cycles work on these kind of small, individual star forming regions. So I just highlight 3 main messages that we got, or the 3 main sort of conclusions we got over the past several years. We saw that star forming regions like molecular cloud star clusters, they are quite aware of what kind of environment they're in, right? So by that I mean they seem to know what kind of galaxies they are in and which sub-region of the galaxy they're in. Are they in the center of the galaxy? Are they in the outskirts, in the arm, in the interarm? They exhibit statistically different behavior depending on their location, right? This is sort of quite cool to see because a lot of the early work on this area is like Milky Way, solar neighborhood stuff, right? So you are limited to one region, and usually people try to generalize their conclusion too far, right? But by looking at different extragalactic sources and look at all the subregions, you can see this is very salient, right? The second message we have got, and this is sort of, again, realized over several rounds of papers, is that we realize the time evolution are quite fast for these kind of individual star forming regions. And by fast is that, I mean the molecular cloud KAM, the star formation happens and feedback dispersed. These all happen within like several tens of mega years. And that is comparable to the dynamical timescale of those regions. So they are never in a quasi long-term equilibrium state, right? They comes and goes very, very fast. And the third thing that we're learning together with this is that it turns out that star formation in star forming regions are relatively inefficient on those kind of characteristic timescales. So on each cycle, clouds, star formation, feedback, over each cycle, they basically convert only around 1% of the gas mass into stars. So what happens to the other gas? Well, they all got dispersed and returned to the ISM. So they have to recycle all over again, right? So this is like inefficient over individual cycles. So basically the long-term galaxy buildup is realized through, numerous cycles of these effects. So that's why galaxies actually doesn't deplete all their gas on this kind of like tens of mega years scale, right? They actually deplete their gas more on gigayear scale, and this is why. So these are the wonderful things that we have learned from this the data set that FANGS has built up. And this has become sort of the foundation for us to really understand how the feedback work, how the star formation happen, and how do we use that knowledge to sort of inform, galaxy simulations, cosmological simulations that people have brought up before. So these are all now possible thanks to the FANGS team. Now, what I want to mention next is that we are not satisfied stopping at FANGS. FANGS is already wonderful, but we are always more ambitious. So one of the directions we're really pushing on now is to do even higher resolution observations. So why resolution matters? Because FANGS give us this wonderful view of a statistically large sample. It can give us individual star forming regions, but sometimes the FANGS resolution isn't enough so that we can resolve the region. So this is a problem. Why? Because without resolving things, it's hard to figure out what is the dynamical state of the structures we're seeing that giving us star formation, how do individual H2 regions grow inside a cloud, and where does feedback deposit most of the energy and momentum, right? These are all important because then they impact the large scale behavior. So this is something we really want to pin down as the next step. And this is what the scales survey now is about. So bear with me, this acronym is only several days old. So there's still a lot of possibility of change, and that sort of label is obviously an AI-generated label, and we may replace it with some other things. So don't come back and blame me if you see something else in a few days afterwards. But the core now is that we now have a new ALMA-Large program following the successful FANGS ALMA-Large program. We have a new ALMA-Large program for the scale survey and a corresponding GWST treasury program that just got approved like 2 weeks ago. So this is all very exciting. And what we are after here is to look at 4 out of the FANGS samples at extremely high spatial resolution, right? So these 4 we have select them to be, spanning a relatively wide mass range, so that we have some level of understanding how does the general galaxy behavior impact all the behaviors. We also are looking at things that have slightly different morphology. So these are important because there are things that happen differently in the centers of galaxies and the things in spiral arms. And with things that are relatively edge on, you can actually probe, some kind of the outflow effect that Laura has mentioned. So these are all in play, right? So we want to make sure we sample still a reasonable range of parameter space so that we can probe all the physics we want to probe. The cool thing here is with the push on the spatial scale, we're now order of magnitude improvement over FANGS and other similar surveys. So here I'm showing you a comparison. On the left is sort of a zoom-in view, a very zoom-in view of one of the FANGS maps for M83. At the middle, this is a new map that I just reduced like a few days ago. And it generates quite some oohs and ahs in our Slack channel, right? As you can see, the comparison here is quite drastic. On the left, you see a bunch of blobs. They might follow like a spiral arm structure, but on the right, you are seeing all these kind of detailed shells, filamentary structures that people are seeing in numerical simulations. Now you're actually seeing it in the actual data, right? So this is quite cool. And the other point I want to make here is that now this is quite exciting because now it gives us the ability to connect to Milky Way work. This has not been possible before because with extragalactic work, usually you have wonderful large-scale, large-scale complex, but you don't have the resolution to actually resolve most of the things. With Milky Way, you have wonderful resolution to resolve everything, but because of the edge-on viewing angle, it's hard to get the large-scale complex information, right? But now we are sort of moving towards the middle point where we are pushing on the spatial resolution. The Milky Way people have sort of figured out ways to construct 3D structures of the Milky Way ISM. So now you can actually try to project it from top down, pretending that you are observing from outside the Milky Way. And now you can see these 2 maps are actually roughly at the same spatial scale. So you can see I'm really starting to see similar structures on the same spatial scale. So this really makes a wonderful opportunity to connect the extragalactic and the galactic community. One last point I want to make, this is again related to numerical simulations. It's important to understand feedback, as Laura has emphasized in her talk. Now we have the ability to really constrain some of the important physics. On the left is the image that we are getting now at roughly 10 parsec scale. The 3 panels on the right are 3 versions of different numerical simulation implementing different feedback physics. And they give you drastically different predictions of how the code ISM should look like on these kind of spatial scales. So now with the data, we can actually compare them systematically with simulations and say which of them seems to have recovered the rough behavior of what we are observing and which sort of feedback model, therefore, they're implementing seems important and worth sort of digging into, right? So this again these are sort of high resolution simulations that are really implementing the really state-of-the-art feedback models. And if we can't get it right there, then it's hard to imagine we can get it right in cosmological context. So this is sort of the large scale, the big picture behind this. Now, with this wonderful scale survey, so this is really sort of our push on the spatial resolution, and this is sort of where we are going after. We are still sort of busily taking all the data and reducing the data, and there's so many data reduction sites that we're trying to activate now because it's like drinking from a fire hose, right? The data is too much volume for us to sort of deal individually. But this is sort of an exciting ongoing process. I want to then quickly highlight a few things that I think are nicely connected to this, but also setting the stage for the next few talks. One of the things we're trying to do now is now we are pushing the spatial resolution. It's important to actually take a step back here and think about the tracer we're actually using. We have been using CO that are detectable from ALMA to look at molecular gas. Now GWST is giving us this wonderful opportunity to look at PAH emissions. So these are polycyclic aromatic hydrocarbons. They are small dust particle. They are permeating the entire ISM, and GWST gave us wonderful maps of them, right? So it would be great if we can figure out how to interpret them. But this is challenging because there's a lot of physics in there. There's heating, there's dust to gas ratio variation, all that we need to calibrate so that we can use these tracers in the most reliable way. These are the things that observers really care about, right? We want to make sure we're not interpreting our data wrong. And this is sort of the direction that sort of Stephen Lunker, who are now a PhD student at UK, are working on. I won't do too much spoiler alert. I would just want to say, there will be pretty pictures like this in his talk. So look forward to that. Another thing we can really do at high spatial resolution is we are now really seeing the individual star clusters popping out into existence, right? So this is, really enabled by, putting down to 10 parsec spatial scale. Now you are seeing the individual clusters emerging from the ISM. Now, the important thing is now with a lot of tracers in different bands, ALMA, CL, GWST, recombination lines, and dust, and all that, we can now actually stream, sort of construct a timeline of their formation. How long does it take for a star cluster to pop out of the molecular cloud? How long does it take for the cluster to emerge and disperse the natal cloud, right? So these are things another student working with me, Neha, will give a talk on. And again, I'll just point you at her talk. Look forward to those wonderful images. One last thing I want to quickly mention, this is sort of in context of another large international collaboration, is that we still haven't lost our sight on the big picture, which is galaxy evolution, right? With all these wonderful things we have learned about the small scale ISM physics, we want to feed it back into galaxy evolution and really understand how the galaxy evolution, become possible due to all these kind of processes. And this is what the MALV team are after. This is multivalence astrophysics to unveil the Virgo environment team. We have built a wonderful data set with a VLT large program, a ALMA survey that I'm leading, and a large HSC treasury that we have landed last year. And here are some wonderful data. And this is going to be in the talk of Faith D'Alessandro, who are just coming up next in the next talk, right? So I think I'm running out of my time. But these are the take-home messages, and I'm happy to address any questions.
Any questions?
Do you need to take out the H for fun now after seeing the S-scales images? Because you are not that high resolution anymore compared to that, right?
Yeah, so we were actually debating exactly what kind of message we want to convey with the acronym. One thing I was advocating for was sense scales. So sense is in this French sense of sense. So no special scale. So we want to push all the way to the end as much as possible. But obviously there's limitation from the instrument side, right? So we got to do what we can. Yes.
Have you looked at power spectra for the kind of spatial power spectra? Because with interferometry data, you sort of have a sweet spot where you see the different scales. So
yes.
Have you compared the FANGs to the S scales yet?
Yeah. So the S scales data. So that bit of data I just showed is sort of the first image we got, which is only one small part of the galaxy, right? So we're in this process of reducing data. But in terms of power spectrum, we have been working on several papers in banks looking at power spectrum of molecular clouds and comparing the cross correlation between clouds and star clusters. And that's giving us a lot of information already in terms of the larger scale organization of structures. Power spectrum is sometimes a little bit tricky because you are easily dominated by the bright spots. So we need to figure out ways to get around that. And there are also like large scale structures like galactic spiral arms that may not necessarily be the information you want to extract out of it. So these are all like at the background. When we subtract it and figure out the right way to tease out information that tells about like exactly how clouds are organized on small scales, I think that's the sort of the information we are after, right? Because that includes imprint of turbulence, feedback, and all that. Yeah.
I'll ask just a very basic question. Just technically, what is involved in getting these data to be at this higher resolution? Is it more time? Is it a different configuration of the dishes?
It's both. So with scales, we are in a good spot where because FANGs has already built this lower resolution baseline that we can leverage, right? So with interferometry, the trick is like you put ALMA into a different configuration. Now it's sensitive to a different range of spatial scales, but you usually like lose sort of a larger scale context. So you need to have something to sort of pin it on the larger scale to make sure the general overall zero baseline is right. Yeah, but this is something that we're just eagerly like combining all the data, and these are usually like terabytes, tens of terabytes of things that we are trying to process. So you can imagine we've created a lot of like space heaters in our office.
Any final questions? And then while we give people a moment to think about that, I think Faith is speaking next. So if you want to come up. Okay. All right, let's do. To Zoom, you can just. So people have been connecting to the Zoom and sharing screens. It's exactly this. Right, so as we're getting set up, next we have Faith D'Alessandro, who will tell us about the MOF project that we just heard a little bit about.
Right. Yeah, so hi, my name is Faith, and today I'll be giving the preliminary results from the MOV ALMA survey that Jai just quickly ran through, and specifically talking about how environmental effects of the molecular clouds cause environmental quenching in specifically the Virgo galaxy cluster. There we go. Okay, so to begin, we must talk about galaxy evolution. So we've already discussed this previously in the last two presentations, but we have to be looking at molecular clouds, which I'm sure is a term that you guys are also hearing by this point. But within these molecular clouds, we have star formation, and particularly the rate at which stars are formed within a galaxy is known as star formation rate. And this is a building block in the galaxy's evolution. The star formation rate basically tracks how the galaxies, the rate at which the galaxies build over time. So Here's a beautiful image of NGC 5643. And this galaxy, you can see, has a bluish tint overall, meaning it's full of young, bright stars, meaning the star formation rate is high in this galaxy. But as galaxies evolve, their star formation rate dwindles, and eventually the galaxy is no longer has the gas to fuel it for star formation, and it's left with just the older generation of stars. We call these galaxies red and dead, which is an example located here, which is a galaxy NGC 4150. As you can see, it has more of a redder tint to it. So what happens when the stars run out of gas or star formation fades? So this is called quenching, refers to the tapering of star formation within galaxies. And we have a couple different types of quenching. We have environmental quenching, which are on scales from 15 kiloparsecs to 1 megaparsec. This refers to the stripping, which is when a galaxy relation happens and the gas is basically just stripped from the galaxy, and stars are no longer able to form. The other one is starvation. Basically, the galaxy is either in an environment that has less gas for fuel to star forms, or the galaxy itself has such a high star formation rate that it's forming more galaxies than gas can refill it. We also have internal processes. This is more of the internal side of the galaxy. So we're looking at stellar feedback and just the stability of the gas in itself. Either the gas is ejected out of the galaxy faster than it's accreted on, or the gas is just so kinematically dynamic that it can't be stable and form stars. So as you can see, we have a basic understanding of the overall effects of quenching and models of quenching on the larger scales, but what we are missing is a development of the scales at a lower scale. We're talking individual cloud scales or molecular cloud scales, which will motivate a better understanding of quenching effects in a galaxy. So this leads us to the MOB-ALMA survey. The goal of this survey is to understand how dense cluster environments drive quenching and influence galaxy evolution. The key capability of this is we're looking at 50 parsec scales, so molecular cloud scales, so you can see what's going on, how are these clouds being affected, and what's driving this quenching effect. So we're using the ALMA telescope, specifically looking at the CO2 to 1 line, 40 late type galaxies in the Virgo cluster. So we aim to bridge the gap between galaxy scales and the cloud scale star formation. So why the Virgo cluster? Well, it's nearby, but it also has a diverse galaxy population. So it has different infall stages, orientations, and environmental exposure, making it a prime place to be looking at the environmental effects. So here is a first look using the Rubin Observatory of the Virgo cluster. Pretty extraordinary, a lot of cool stuff. I am not involved in that, but very cool and exciting. Okay, so here are the main questions being addressed by MOB-ALMA survey. Do the environment shape the molecular cloud and spatial distribution? Do cluster galaxy show kinematic signatures of environmental processing? And what drives variation in star formation efficiency? So I will be addressing the first question today in this talk. Again, we're preliminary results here. So here is a beautiful example of our survey. So you can see right off the bat, the resolution is extremely high. We can see individual clouds areas and just very exciting, like what Jai was showing earlier. But if you look really closely, you notice that there isn't all 40 up here. We, again, like I said, preliminary, so we're not done resolving all of the data yet. So we have put all of the galaxies that we have finished up here. So let's take a deeper look and look at one of the galaxies in our survey, IC 3392. From this galaxy, we extracted the maps of the integrated intensity, the line of sight velocity, and the velocity dispersion. So right off the bat, we can get a lot of information just from these spatial maps themselves. And again, we are looking at 50 parsec scales in this example. So really high resolution, really cool stuff. But particularly, another great example is this galaxy pair in our survey. So this is NGC 4567 and NG 4568. So another great example of cool information we can get from these maps, particularly whether they are actually in relation to each other or if they're just front and back of each other. But diving back into IC 3392, from this data, I plotted the velocity dispersion over the integrated intensity. This scatter plot will hopefully give us information of the dynamical state of the molecular gas within this galaxy. And once again, highlighting that we're looking at 50. So the first thing I did was plotted the viral parameter. So the viral parameter is essentially the relation between the kinetic and gravitational energy. Specifically, the viral parameter of 1 is a gravitationally bound object. It'll likely collapse versus a viral parameter of 2 or higher. It's unbound and unsupported against collapse. So you can see right off the bat from our data, the scatter plot shows that most of our data is not only above the viral equal to 1 line, but it's above the viral equal to 2 line, meaning that these clouds are not in a state of collapse and actually very high in a kinematic state. The next thing I did was plot the turbulent pressure lines. So the turbulent pressure just indicates the dynamical state of the gas, so specifically looking at the motion turbulence of the gas. So I plotted the turbulent line from 10 to the 3 all the way up to 10 to the 8th, but in this scaling, you can only see the 10 to the 3 to 10 to the 6 lines. And as you can see, the data spreads along across all of these lines, indicating that there's a broad distribution of gas conditions across this sample. So the results, we have a majority of data points above the viral equal to 1 line and the viral equal to 2 line. And also the galaxies are in a wide range, diverse physical conditions of cloud at cloud scales, or showing that there's a diverse physical conditions at cloud scales. So interpretations, these clouds are not strongly self-gravitating and not yet in a state of collapse. So future work, we're trying to connect these results to the full survey and looking at the different positions of infall correlated to that, to these galaxies, to see how the different stages of infall affect these results, and also correlate the relationship between the molecular gas properties and the star formation rate to see how the environmental effects affect the environmental effects of the galaxy affect the star formation rate. And then long term, we aim to compare these results from the MOV-ALMA survey to the FANGS survey in order to correlate how cluster environment galaxies and their environment affects the results compared to galaxies outside of a cluster. And that's all I have for you. Thank you so much.
Any questions for Faith?
Question.
Yeah.
On your plot, the bottom left, there's that weird cutoff.
Yeah.
Could you explain that a little bit? Is that
I have a slide just for that. So this is the we call it the quantization effect of our data. So basically, ALMA has a spectral finite channel or velocity channels. So some of our data is only getting 1 to 2 channels per beam. So this leads to a discrete step-like line with measurements. So we did do a correction here. So it was the took the observed square or the squared observed minus the channel, and then quadratic. So we tried to fix it, but there is a limitation to make it discrete like this.
Any other questions?
I have one.
Go ahead.
So is this galaxy in the center of the cluster? Is it feeling the tides, or is that? So
A great question. I don't know right off the top of my head. We can see, yeah, it's a smaller one right here, so it's definitely on. I'm not sure what the environment is surrounding it, but we definitely know it's on the smaller scale than versus the other ones.
So the things that further to the right are the galaxies that spend more time in the cluster. So this one has already passed its first pericenter passage, has been in the cluster for a long time. That's why the gas disk is so truncated relative to the starlight. So most of the outer gas has been stripped.
the whole dynamical state. Influenced by that,
Yes. Yeah.
but also seeing it at the molecular cloud size is kind of cool.
Yeah.
Any question from Menno?
I was wondering if we could really have information on the galaxies that you can only see on the edges. Like you have, for example, this galaxy right there.
Yeah.
Can you do something about it, or
Do we do something? I'm sorry, what was that?
can you have some information about it?
Yeah, we well, actually, it's very limited, but we can extract, very limited amount. It's not as pretty of a plot, if anything.
Not suitable for the type of analysis space is doing, but we have a graduate student at Ohio State who is exactly looking at this kind of galaxies. And the cool thing you can do is measure the scale height of the gas, which you cannot do for face-on galaxies. And that's again important because how thick it is depends on how much energy you put in to drive the turbulence. So yes, it's definitely got going. Yeah.
With these here, then I know that the deeper we've looked at elliptical galaxies, the more the evidence there's been for often disk components, a bit more dust and gas than we'd usually thought. Are there any ellipticals in the survey here, and have you found much of anything from them?
I personally haven't looked through the survey as intensely as others, so I don't know if Jaid has, like I said, it's very preliminary. So
this one, the sample is focused on disk galaxies. So we intentionally didn't include elliptical because we know there will be a bunch of non-detections for most of them. But I think you're absolutely right. There are dust and gas that appears as disks in ellipticals, and it's interesting to ask what's their origin and how does the gas behave in there. Yeah, it's just not the focus of the survey. Yeah.
Any final questions? All right, let's all thank Faith again. Next. If you're logged into the Zoom, you'll just share it there. I'll wait at you for 5 minutes after. You can just share screen out of the Zoom call.
And make sure you share the screen.
We'll let you know if you don't.
Share the screen.
I shared one. That's used to share.
I don't.
Says
Yes, it is. Yeah.
Is this shared? Okay.
Yep.
Okay, cool. Guess I'll go ahead and get started. Hi, everybody. My name is Stephen Lanker. I'm a first-year graduate student at the University of Kentucky. And I'm really happy to be here to present some very preliminary results on a galaxy known as the Evil Eye. It's officially Messier 64. And specifically looking at this galaxy with ALMA and JWST. So yeah. So some motivation for looking at this galaxy involves the James Webb Space Telescope. So in particular, we want to look at galaxies with the James Webb Space Telescope with looking at PAH data. As Jai mentioned in his talk, he talked about how we have many beautiful new imagery of PAH maps with all these nearby galaxies that take very little time to get with the new James Webb Space Telescope. And the thing that is important about it is we want to look at PAHs, or polycyclic aromatic hydrocarbons. That's the only time I'm going to say it because it's a mess. So I'm just going to refer to it as PAHs. I should have said that earlier. The reason why it's important is because we aren't super sure yet on how PAH data can relate to information about the interstellar medium, or ISM. So that's a big thing we want to look at in these nearby galaxies with this new JWST data that's very high resolution. The thing that makes it difficult to directly trace PAH as an ISM tracer, in a sense, is the fact that PAHs are destroyed by high intensity radiation. So UV and stuff like that, higher end stuff, or higher ends of the electromagnetic spectrum. So we want to utilize like different modes of analysis, like ALMA, which I'm about to talk about. But as a quick little comparison, this is the galaxy M51, and this is Spitzer data on the galaxy. And as you can see, this is a PAH map of the galaxy, and you can see it's very beautiful. This is quite a nearby galaxy. It's around 7 megaparsec away, if I recall correctly. And you can see a lot of interesting features, the spiral arms. There's a lot of clusters within the arms, and there's a very bright spot in the middle. And thanks to the JWST Feast group, they took a look at this galaxy, and we can overlay an image they got of the same exact galaxy. And you can see how much higher resolution and much better detail you get in this image of M51. There's a lot more striations in the spiral arms. There's a lot more just general detail you can take a look at much higher resolution scales. So going into it, we want to compare PAH maps to things we already have a better understanding of when it comes to the ISM, i.e. CO, like Jai talked about, which is a cold molecular gas tracer. So with this new high resolution JWST data, we can combine PAH maps with CO maps and overlay them to see how PAH can relate to the ISM much better. Now, a quick comparison of the same object. This one was talked about in the earlier talks. NGC 628. This is also a nearby galaxy. On the left is the ALMA molecular gas CO 2:1 data. And on the right is the PAH map of the same galaxy. And when you compare the two directly, you can see that there is some overlay between these two maps. You can see that there's a relationship between them, at least just visually. You can see a very general trend here. And the big difference between these two things is that the PAH map took around 5 to 10 minutes of observing, and the CO 2:1 map took 10 hours, or on that order of 10 hours, to get the same map. And also, as you can see, this is lower resolution than that by a pretty significant margin. So it's incredible what we can get with the JWST data, and of the same exact object, the same distance away. So the FANGS team, or a specific group within the FANGS team, led by Ryan Chown and Adam Leroy from Ohio State, looked at 70 nearby galaxies because they wanted to characterize the relationship between the cold molecular gas given off by CO and the PAH data from JWST. And they found that they found that they are nearly linearly correlated. So on this plot, the y-axis is the intensity of the cold molecular gas, and the x-axis is the intensity of the pH. And you can see that there is a nearly linear relationship between the two. So where there is higher intensity of carbon monoxide, there is a higher intensity of pH. Yeah, and they have it's almost a one-to-one correspondence, and this is a plot of all of these galaxies. Additionally, the nearly face-on within 20 megaparsecs, and all of these galaxies are relatively massive and star-forming disk galaxies. They have disks. And when you plot all of them individually with a running median, so you can see that and when you combine this with specific star formation rate, you can see that there is even an implied relationship between the star formation rate and the ratio of carbon monoxide over pH, which is very interesting to see. The higher up, you can see a general trend of the higher up you are here, there is less star formation rate than the lower down. And so the idea of this talk is that we're looking at a very specific nearby galaxy, M64, which is not a part of this analysis in this paper. Now, why M64? This galaxy is very, very close. It's 4.4 megaparsecs away, which is a lot closer than, or much closer than a lot of the galaxies in the paper by Chan et al. This makes it a prime target for JWST's pristine resolution. With the MIRI, you get a JWST scale of roughly 20 parsecs. And with ALMA scale, the ALMA resolution scale is roughly 30 parsecs. So this provides a much higher scale resolution than anything before, even the state-of-the-art like Spitzer before. And this galaxy has many unique properties as well. There's evidence that this is a post-merger galaxy. Just physically looking at it, there's very thick, dusty surrounding torus around the core of this galaxy, which by default, it has higher gas densities within it. And there's some specific properties about the rotation of the galaxy as well overall. But yeah, this makes it a very good candidate for looking at pH and comparing it to the ALMA data we have already on this galaxy. So utilizing the same method of analysis as Chan et al., I looked at CO 2-to-1 and 3-to-2 transitions to compare them. In this plot I've generated, this is the intensity of the 2-to-1 emission on the y-axis and the intensity of the pH on the x. So it's the same general plot. And you can see it looks very similar to the previous data as described by the 70 galaxies. You can even, the color plot also is the 3-to-2 to 2-to-1 ratio. So you can see a general gradient going towards the top right that characterizes how that changes, where there's more 3-to-2 emission compared to 2-to-1 emission, which is just higher energy emission. Now, or characterizes higher energy radiation fields surrounding this region. Additionally, when you plot both of them together on the same plot, you get this, which shows the 2-to-1 emission is in the blue, and in the red is the 3-to-2 emission. And you'll see lower overall intensities in 3-to-2, which is expected because overall you would expect to see lower intensity emission throughout the galaxy, a lower amount of higher intensity emission, throughout the galaxy. But you'll notice at the top right, and in this plot you'll notice it as well, you'll see it rises above that best fit line, and it rapidly rises to meet with the CO 2-to-1 emission. And that is the that is the galactic core. That is the galactic core. So that data up there is going to rise higher and be above the best fit line because the galactic core tends to have harder radiation fields, which leads to higher energy emission. So what's next? Temperature and optical depth can be taken out of this data. And so since PAH cannot survive highly ionized environments, we want to also take a look at H alpha, Passion alpha, and bracket alpha data, which H alpha is provided by a Hubble Space Telescope, so we can even look into Hubble Space Telescope data. And Passion alpha, bracket alpha is given by JWST infrared emission that we can look at as well. And we can compare other wavelengths of PAH emission as well. So in this talk, I specifically utilized the 7.7 micron wavelength for PAH emission, but there's many other modes of PAH emission or wavelengths of PAH emission, excuse me, which include like 3.3, 12.7, and there's a couple others in there. Can't remember them all off the top of my head, but yeah. So that would be very interesting to take a look at as well. And then we more in-depth look at specific galactic regions is also necessary because the difference between the galactic core, the spiral disk, and the more diffuse regions and H2 regions is apparent with the ratios. So a quick summary, JWST is providing a very high resolution of PAH maps for nearby galaxies, and combining with ALMA-CO maps will provide insights on the relationship between these molecules in the ISM. The galaxy of M64 is a prime target because of its closeness and its unique properties, and the results from M64 are consistent with the 70 other nearby galaxies that we had Brian Chown and Adam Leary took a look at. So yeah, that's about all I have. Thank you.
Any questions for Stephen?
Yes.
So you mentioned the possibility of looking at other lines for PAH emission.
Mhm.
Are they subdominant? What fraction of total PAH emission is in the line you're looking at compared to what you expect to still be out there?
That's a great question. I'm not quite sure. Wait, hang on. Your question was which PAH lines would you expect to be more dominant in? Or
So I know almost nothing about the field. So you
Yeah,
said
yeah.
there were a handful of lines or so, and you looked at one specific line.
Mhm.
I don't know if that's because it was the easiest or because if you look at all the lines PAH could come out of, that one has 60% of the total
right.
emission.
Okay, so for PAH at 7.7 micron specifically, we wanted to look at 7.7 because there are a few differences in how 7.7 micron PAH emission compares to the 2:1 and 3:2. In particular, the PAH emission at 7.7 microns has it's affected by external radiation fields more so, and that allows you to distinguish between the different regions more easily. So galactic cores will have harder radiation fields, and you'll see those features in this plot. In these two plots, you'll see how it rises above. You can distinguish the galactic core from the rest of the galaxy. So yeah, that's the main reason we took a look at 7.7 micron.
Maybe a similar question, just because I'm curious. What makes the PAH observation so much more quick than the more detailed mapping, like minutes versus hours? Why is it so much faster?
So that's James Webb Space Telescope. That's something to do with the James Webb Space Telescope that I actually don't quite I can't quite answer off the top of my head.
It's not affected by the atmosphere.
Mhm.
It's in the infrared where we know much better how to build better detectors. You also don't need to combine multiple configurations like you do for interferometry. So all that adding together.
So that more detailed mapping is coming from like ground-based interferometry.
That was ALMA.
Alma,
Ah, okay, I thought they were both.
I
I was observing different lines with both with JWST for some reason.
I removed the
That makes-
picture. Oh,
Okay.
sorry. Continue.
I was just gonna say, so it's JWST being way faster than ALMA.
Yes.
Right.
Not observing PAH with JWST being faster than observing other lines with JWST. I misunderstood that, sorry.
Yeah, ALMA, I removed the picture, but ALMA, yeah, it's a ground-based telescope
That makes
versus
perfect sense.
JWST, which is all the way out there, right?
Yeah,
So,
yeah.
yeah.
Cool.
But yeah.
Right, let's thank Stephen again. And Saja is next. Do some sharing screen that way.
yeah, make sure you share the screen.
Can you share? Yes. I just need to move this. So if you go to your bottom left, there's a little slideshow picture.
Okay, hi everyone. My name is Sajishar Neha. I go by Neha. Thank you for coming to attend my talk. I'm talking about a completely new topic you guys have never seen before today at all. So today I'm going to be talking about multi-wavelength radio continuum observations of young massive clusters in nearby galaxy centers. It's like a tongue twister. And I'm advised by Jay Sun at the University of Kentucky, where I'm a post-bac scholar. Okay, so before I get into the details, I want to give you a bit of information about what young massive clusters are. So they are very compact, massive regions, massive compact extreme regions in nearby galaxies or our galaxy in the universe in general. They're extremely dense because they are places where many, many thousands and millions of stars are being born. And in order for that to happen, you need very dense, very high pressure environments. And as I mentioned, because it's high pressure, you have high gas surface density and also intense radiation fields that are getting emitted from the forming stars. And I also mentioned it before, but it's a stellar nursery where thousands to millions of stars are being born. So I chose to study YMCs. Why did I choose it? So because they're local analogs of high redshift star formation. For example, you want to understand how the universe was in the past when all of it was like a YMC environment, very dense. A lot of star formation was happening. By studying YMCs in the current stage in nearby galaxies, we can infer that information because high redshift observations, of course, are difficult and harder to get high resolution data of. They also give us an idea, a window into how star formation occurs, the different evolutionary stages, and basically what mechanism is affecting or driving the star formation or disrupting it. And it can also give us information about how clusters can disrupt or disrupt or evolve other cluster progenitors. And then by studying YMCs, we can build a statistical census across different environments of star forming regions. And now that hopefully I have told you guys how awesome YMCs are, what slide is it changing? Okay, we're applying YMCs. So we can find YMCs in many different places, but in this work, I'm choosing to focus on nuclear rings and bar spirals because of the stellar bar in these bar spiral galaxies funnel the gas inward, which creates elevated gas surface density and leads to intense and sustained starburst. There are a few other regions where you can also find YMCs, but because they are a bit rarer and harder to detect with current observational instruments we have, the nuclear rings offer the best balance. They are nearby, they're abundant, and also observable with radio instruments we have, like ALMA and VLA, at quite high resolution. So why ALMA and VLA? So ALMA and VLA, I put some really nice photos of them here. I'm using new and archival data from ALMA, specifically 93, 107, 225, and 350 gigahertz. And for VLA, we're using 33 gigahertz data. And this is because many young massive clusters are embedded in massive dust rings that are not penetrable by optical telescopes and IR telescopes. But the radio continuum is unobscured by dust, which allows us to look in greater detail into specific clusters and separate them from their surrounding bright sources, as you will see in my plots up next. So for this work, one of the galaxies I'm focusing on is NGC 3351. It has a really beautiful, bright central ring. It's about 10 megaparsecs away from us, and it does not have a central AGN. And as I mentioned earlier, I'm utilizing ALMA and VLA data across multiple bands. And why do we need multiple bands? Because multiple bands give us information about different components that are part of that cluster. Because as you have a cluster, you have dust there, you could have free radiation there, you could have synchrotron radiation there. So here in the plot, I overlaid the different bands. And the noise distribution is different because some of them are new data and some of them is archival data. And I also have, again, information about the primary tracers that I just mentioned. And how do I identify the young massive clusters? So I do a peak finding run. I find the brightest peaks that are above a signal to noise ratio of 3.5. And I require it to be present in multiple bands. And I cross match it according to their right accession and declination to make sure that they're part of the same cluster system and not a different entity altogether. And this is a JWST image of the same ring that I just showed you earlier, but this is just different colors. Okay, great. And then I do a 2D Gaussian model fitting for each band to extract their flux measurements. And with that flux measurement, we can create a nice spectral energy distribution or SED plot. And each of the band, as I mentioned, like 350 gives us information about the dust, 225 gives us information about the dust, and free 93 gigahertz gives us information about the free, 33 can give us information about the synchrotron radiation. Okay, great. So why those 4 bands? So this plot, clearly you've not seen it before for the 3 more talks. I just modified it a little bit. So in the beginning, you have the molecular cloud, so you have a lot of dust and gas. That's bright in 350 gigahertz. And then as it evolves and more stars are being formed, you start getting free radiation, which is visible in 225 and 93 gigahertz. And as stars evolve, massive stars evolve and they eventually die, unfortunately. So you have, unfortunately, fortunate. I like supernova remnants. Okay. So when you have supernova remnants supernova happening, the synchrotron radiation from them shows up at 33 gigahertz. So that's my justification for all the 4 bands. And this is a nice schematic. Okay, great. So for one of the sources, I'm showing you how I'm creating the SED plot and how it helps us. So first, as I already mentioned, that this cluster is just being born and fully embedded in dust. So most of the radiation will show up here. And then as it evolves, you have more emission in the lower frequency bands. And as you go forth, it turns out to have emission either in all 4 bands. It really depends on how the component structure of the cluster is made up. But basically, this is like the evolutionary stage of how the cluster is evolving. And then with all these band data, we can create a nice model fit. So to help us track the component fraction from each of these bands and get a better picture of at what specific stage of evolution that specific cluster is in. So for example, here you have 2 different sources. As you can see, the curves are quite different, right? So when you have a significant enough synchrotron percentage, then that means that it is a very high likelihood that you have a supernova remnant there. That means that cluster is going to be older. If you have a very high dust emission, the thermal dust emission, that means that cluster is younger. And then I also extend the study into NGC 1097, which is another really beautiful galaxy who has a much brighter ring, but it also has a very bright central AGN. Still, we do detect a lot of the clusters with noticeably high signal to noise ratio. And I just wanted to show you this photo because I made this photo and I felt like we're really fortunate to be able to study such beautiful structures in the universe. And we just look at them and they're so far away, and I just really liked it. So why not? It's there. Great. And this is what the ring looks like in ALMA. As you can see that compared to JWST, you can much clearly see each of the clusters in the ring. That's why, of course, ALMA is important because it helps us detect the specific clusters and derive information about them. But my studies of this galaxy is still preliminary, so I'm going to show you just a preliminary plot. We're still waiting on the VLA data for this galaxy. Once we have that, we're going to be able to create an even better model. And what we can derive from the SED modeling, we can derive the stellar mass, the gas mass, the virial mass, the ionizing rate, the principal size, and the cluster age of that specific cluster. And what do we have going on in the future? So our ultimate goal is to constrain the complete timeline of the young massive cluster evolution. And in order to do that, we plan to build a multi-galaxy sample, including the two I mentioned and other nuclear ring galaxies, to sample all the evolutionary stages and measure how long does a cluster spend at each evolutionary stage. And also, as I mentioned in my sample, there's one galaxy with an AGN, there's one galaxy without the AGN. So by studying the YMCs in those two different settings, we can get more information about the AGN feedback on the YMC evolution by comparing them as their distance from the AGN and the rate of evolution for different scenarios. Okay, in conclusion, I told you why I'm studying young massive clusters, because they probe star formation in, they're probes of active star formation in galactic nuclei. They are drivers of ISM feedback, and they can constrain the star formation history through cluster ages. And this work, I detected YMC candidates in two galactic nuclear rings, and I measured their fluxes and completed the SED analysis, and I'm working on deriving their fundamental properties. And going forward, we're planning on building the census to have a better understanding of the evolutionary timescales and AGN feedback on these young massive clusters. Thank you so much.
Questions for Neha?
I wondered if you see any young star clusters like before supernovae that have synchrotron.
Yes, I don't have that plot here, but we did find some of the, so as I mentioned here. This is my first time using PowerPoint, so I'm like super confused. Here, as I mentioned that 15 of the 28 sources show synchrotron, so we are yet to look into detail into how many of these are actually in the supernova stage and how many of them are just showing synchrotron radiation. But you're absolutely right, that doesn't always mean supernova. So this is specifically for 3351.
Yes, dust emission, my wheelhouse. So there's talk about the submillimeter excess, for example, with dust. So how do you model the dust emission here? Is it a fixed temperature, or is it surface density? What do you put?
Yeah, so I know that in SED modeling there are a lot of factors that go into play. As I'm building on it, first I fix the value of alpha sometimes, and then after I fix the value for different sources, get different values, and then I let it free kind of to see how that works into play. Sometimes the models are not really good, but density fitting is a long and lengthy process, and I hope that answered your question.
Curious what temperatures you got.
The temperature I have not really
Because it doesn't turn over. I had to flip this whole thing in my head.
Yeah.
because I work in wavelength, but because you only have 2 points, I assume you had to fix a few things.
Yes, yes.
What you were fixing, or if there were points. I had to look up what the shorter wavelengths were in ALMA speak.
So band 3.
Yeah, so band 8, 9, and 10, if those are coming, or
I wish, I want all band data. I don't know if Alma wants to give me all this data.
probably not. They're mean, but it's really cool.
That would be really great to know, but yes, I did, again, this is preliminary work, we just started working on it, but I do know the steps of deriving the temperature for each of the thermal sources, and I'm working on them, so.
That would be very, very interesting.
If you give me your email, I will reach out to you
Sure thing,
and invite you about it.
Lovely talk, yeah.
Other questions?
So this is very much not my area, but so you mentioned that studying these clusters was like interesting because they're analogs for like early star formation. Can you say a little bit more about like why finding clusters is like why these rings are a good place to look for those
Yeah,
analogs?
of course. So, because maybe this. In the early universe, because everything was like jam-packed together, you had a very dense gas scenario, right? So I look at the nuclear rings because in barred spirals, the gas, because of angular momentum, funnels inwards. So when you have a lot of gas, you have that dense scenario, right? So that kind of mimics what the universe looked like in that past stage, where everywhere was dense gas. So even though it's not the exact same, because early universe was metal core, different, it's still relevant. But that is also another thing, metallicity. I know that it has some kind of effects on star formation, but I didn't look into detail. I am aware.
Yeah, thank you. Any last questions? Thank her again.
Thank you.
And then next up we have Evan Jennerden. You. Screen, and I can confirm that I see the screen on Zoom. Perfect. All right.
All right, so I'm Evan Jinnerjohn. I'm a PhD candidate at Ohio State. I'm advised by Michael Tucker and Chris's. And so today I'd like to talk to you a little bit about supernova 2023 UFX. This is the lowest metallicity supernovae that we've detected so far. But before I do that, I'm first going to walk you through what a typical core collapse supernova looks like. Take typical with a grain of salt, because every supernova is special in its own way. But I'll do that with a combination of some real light curves and some modeled spectra. And so the real light curves I will show you come from 2023 IXF. This is probably the best studied supernova since like 1987A. And that's because of where it went off. It went off in M101, which is the Pinwheel Galaxy. It's a very well-studied galaxy, and it's very close. It's only about 6.5 megaparsecs away. And so because it's so close, we've been able to get a lot of nice follow-up spectra deep into its nebular phase. This is the light curve for 2023 IXF, and you can split up these light curves into 2 main phases, the first of which is the plateau phase. So the plateau phase of the supernova light curve probes the hydrogen envelope. At this point, the hydrogen envelope is expanding, but it's still optically thick. We can't see through it yet, and so we are just seeing the hydrogen envelope itself. And at this point, it is powered by hydrogen recombination. And that hydrogen recombination gives it a fairly constant luminosity, hence the name plateau phase. And the duration of how long this lasts gives you an idea of how massive the hydrogen envelope is for the progenitor star. And so that typically is like 50 to 100 days long. For IXF, it's closer to 50 days. And so for IXF, the hydrogen envelope was like 4 to 5 solar masses, just to give you a reference point. Then the spectra you take in this phase are also still probing the hydrogen envelope. And there are a lot of things you can learn from this, but the main thing that I want to point out are these metal absorption features from like calcium and iron and other things. If you're seeing metal absorption here, that is metal from the progenitor star itself, not from the explosion. It's from the progenitor star and it got mixed into the hydrogen envelope, and that's why we're able to see it here. So any metal absorption you see indicates that that star had metals during its life. The other phase you can probe is the nebular phase. At this point, the hydrogen envelope has become optically thin, so you are now probing the core of that massive star itself. And at this point, you're not powered by hydrogen recombination, you're instead powered by the radioactive decay of cobalt in thigh. So these are what the spectra look like in this phase. Once again, there are a lot of things you can learn from these spectra, but I'll just focus on a couple things. First of all, the emission profiles of these lines give you an idea of the velocities of your ejecta. And then additionally, this oxygen to calcium ratio, because we're probing the core at this point, the oxygen gives you an idea of how massive that CO core for the star was, and thus in turn gives you an idea of how massive the progenitor star as a whole was. So you've seen what a typical supernova looks like. Now I will walk you through why 2023 UFX, this really metal poor supernova, is so weird. It's really unfortunate I went after the FANGS people because all my pictures will look very lame. This supernova went off in October of 2023 in a very dweeby, tiny little dwarf galaxy. It's only a kiloparsec across. It went off on the outskirts. And so it's exciting that it went off on a dwarf galaxy because we know dwarf galaxies are pretty metal poor. And so to just kind of ground you, this is the mass metallicity plane of a bunch of different galaxies. And all the way up there on the top right, that's M101, where IXF, the light curve I showed you, that's where that went off in. So you can see it's a very massive galaxy, like 10 to the 11 solar masses. It is very high metallicity, like around solar, actually a little bit above. And then all the way over here on the bottom left, that's where the host of 2023 UFX is. It's around like 10% solar, and it's not very massive, closer to like 10 to the 6. But the reason that we care about these low metallicity supernovae is that we know now from JWST, it's confirmed that there is a metallicity evolution with redshift. So all of these red points are galaxies that were observed by JWST. And you can see that for being at the same stellar mass, they are significantly lower metallicity. It would be awesome if we could study the supernovae that go off in these distant galaxies, but that is very hard to do. Really, the only shot you have is if some chance lensing event happens, which did actually happen very recently. There was a Nature paper on a supernova at like a redshift of 5, but it's still really hard to do. We don't get lucky that often. So instead, what we have to do is study these supernovae that go off locally, but in these metal poor environments, like 2023 UFX. But there's really only like a handful of these right now, like 4. And so this image I showed you before, this comes from Michael Tucker's paper in 2024. And one of the weaknesses of his paper, I'm allowed to call it a weakness because he's my advisor, is that he used all archival imaging to fit an SED and get an idea of the massive metallicity of this host. Where I come in is I had some time on the Large Binocular Telescope in Arizona. So I went and got deep photometry in the UV-VRI and JH and K bands to perform a much better SED fit and better constrain some of the characteristics of the host galaxy. So this is the plot I showed you before. After my new SED fit, the host of 2023 UFX goes from there all the way to down here. So we actually now think it's closer to like 1% solar metallicity, which makes it way more exciting. And now this is the light curve of 2023 UFX for the supernova itself. You'll remember one of the first things that I told you was that the length of the plateau phase gives you an idea of how massive the hydrogen envelope is. It's typically around 50 to 100 days. 2023 UFX, it's actually closer to 20 days. So we think this means the hydrogen envelope is probably closer to like a single solar mass. But that's weird, right? Because the way you make a hydrogen envelope less massive is with stellar winds. You strip it off. But how, like your mass loss rate is dependent on your metallicity. And so at lower metallicity, you would expect to have a more massive hydrogen envelope. The only way you can get around that is if your progenitor star was very massive and therefore very luminous and was able to strip it more efficiently. So we take this to mean that the progenitor for 2023 UFX must have been pretty massive. And then, so this black is the model I showed you earlier for this phase. The blue is the actual observation of 2023 UFX. And both of these are 31 days after explosion, so they're very well matched. And I pointed out these absorption features earlier. Look at how deep they are in the model spectra compared to how shallow they are. I mean, you can hardly even see them for the iron in 2023 UFX. So this is just kind of more confirmation that this was a very, very metal poor supernova. And then next, remember the nebular phase, where now we're actually probing the core of the progenitor. And once again, the black is the model, the blue is the observation of 2023 UFX. And you can see they do not really look alike at all. So I'll point out a couple things here. The first is that oxygen to calcium ratio. That gives you an idea of the progenitor mass. Typically, it's like close to 1, which would correspond to like 10 to 20 solar masses. What we're seeing here is closer to like 2 or 3, which is another indication that this was a very massive progenitor, like closer to 20 to 30 solar masses, which aligns with what we saw in the plateau phase. Another thing to point out, since I'm talking about oxygen, is this velocity distribution. In the model, right, you just see that one peak and that's it. But in 2023 UFX, we're seeing these 3 distinct peaks, which is interesting. What we take this to be is some sort of asymmetric explosion, basically, where we have one bulk component coming pretty closely aligned with our line of sight towards us that gets blue shifted, and then one that's red shifted going away from us. And every supernova explosion is asymmetric to a certain extent, but one way that you can become much more asymmetric is if your progenitor star is quickly rotating. So that's what we interpret this to mean, is that the progenitor must have been a fast rotator. And then the last weird thing I will talk about for this supernova is this. So these are the last 4 spectra that were taken of 2023 UFX. They range from like half a year to a full year after explosion. And in these first 3, you can see this like boxy H alpha emission, which is normal. You expect to see H alpha in a supernova explosion for like decades after it initially explodes. What's weird is that that seems to disappear for us. Instead of that boxy emission, we just kind of see this downward slope. So what happened to H alpha? We do not know. Our best guess is that maybe there was a change in the mass loss rate of the progenitor, where for the last phase of its life, essentially it was losing more mass, and therefore the circumstellar medium closer to it was more hydrogen rich. And to get a rough idea of when that mass loss change would have had to occur, we can use this equation and then just plug in, like assume it disappeared halfway between these 2 spectra, some typical wind velocity, and then use R ejecta velocity. That's like on the order of centuries before explosion, which is not a time scale we talk about a lot in astronomy. So with that, I'll leave you with my conclusions. 2023 UFX is a weird supernova for a lot of reasons, but it's important to study it because of how low metallicity it is. And it can give us some indication of how supernova have changed with redshift, and supernova affect things like galactic feedback that we talked about earlier today. So it's important to study things like this. But I'm happy to take any questions.
I want to ask you the mandatory supernova question. Do you guys see any binaries?
No, we don't. So that's another thing that maybe could have to do with the H alpha disappearance, is a weird binary alignment. And so we know, I mean, supernova come from massive stars. Massive stars love to live in binaries. They don't care how close the binary star is. They don't care how massive the other star is. But I believe still currently, we have never actually confirmed after a supernova went off that it is within a binary. And that's true here still. We don't see any binary companions.
Any?
I have a very basic question. Can you tell the distance now?
Yeah, so we can get the distance from the spectra and just fitting like what redshift it has to be at. So it's at a redshift of like 0.015-ish.
But does the supernova give you a distance as well?
Yeah, so that's fitting the spectra to the supernova. That is how redshifted the spectra of the supernova.
Oh, so it's just the redshift of the supernova,
Yeah, which aligns with where the galaxy is.
Okay.
Not the luminosity distance.
Correct.
The supernova itself.
Yes.
Like supernova 1As you can use for distances. But I thought you could use supernova type 2 as well.
I don't think so. It's energies vary enough that you can't quite use it for that.
That was my stupid question. Can you give me this luminosity?
Any other questions? All right, let's thank the speaker.
There's pizza, so we have, okay, just to explain. We have barbecue chicken, we have buffalo chicken, we have pepperoni, and we have veggie. Okay, No cheese pizza because that's for 4-year-olds, right? I think.
One quick note, I'm gonna let you eat and relax and all that kind of stuff. Around 12:30, we usually use this time also to talk a little bit about just kind of society business as well. There's just like 3 little kind of informal things that I'd like to talk about,